This lecture, section 2.1, is about increasing, decreasing, and piecewise functions. Starting with definition of increasing and decreasing functions. On a given interval, if the graph of the function rises from left to right, it is said to be increasing on that interval. If the graph drops from left to right, it is said to be decreasing. If the function values stay the same from left to right, the function is said to be constant. So graphically, what's going on here? If we draw, oops, we're going to start with an increasing function. We're going to pick 2 points on this function. And we're going to label the x value of one of them A and the x value of the second one B. So then we have the y values f of A and f of B. And you can see as you go from the point A, f of A, to B, f of B, the y values are going to increase. So formally, the way we write this, if f is increasing, on the interval a to b, with a less than b, then f of a is less than f of b. And similarly for decreasing, again, choose 2 points, label them a and b on the x values. So then we have f of a and f of b. And this time you'll notice that the y values decrease. And finally, if they are constant, constant function is going to be our horizontal line. you'll see that no matter which 2 points we choose, the y values are going to be the same. When we're talking about increasing and decreasing, it's also important to talk about relative maximum and minimum values. Suppose C is in the domain of F. Then f of C is a relative maximum. If there is an open interval containing C. Such that f of C is greater than f of X. For any X on the interval. F of C is a relative minimum. If there is an open interval containing C. Such that f of C is less than f of X. For any X on the interval. That's a bunch of math jargon. Let's go ahead and see a real, like a graphical example of this. Let's say we have this function here. So starting with the relative maximums, maxima would be the plural of maximum, so it would be the relative maxima. It's any point where we can find a little area around that point, a little interval. So if I choose this point here, you'll see if I find a little interval, I put it in parentheses, soft brackets, around that maximum there. And it is the tallest point in that little maximum. So we don't care that it's the tallest point on the entire graph. We just care that it's the tallest point in its little area. So if I label this x value C1, then f of C1, because this point would be C1, f of C1, would be a relative maximum. And then we have one more here at this point here. This would also be a relative maximum. Then the relative minimums are going to be anywhere where it's the smallest point on that little interval. So you can see the little interval made there. This point here, let's call it C3. That means f of C3 is going to be the minimum. Notice how I'm always using the y value to answer this. Whenever you're asking for a maximum or a minimum, you want to think, if I told you how tall the mountain is, would you give a y value or an x value? The height of the mountain is always going to be given by a y value. And then even this point right here, even though it's a sharp point and it's weird, the graph kind of changes there. That is still a relative minimum because it is still the smallest point in a little interval around it. I also want to point out here that we have a maximum which is smaller than a minimum. And that is totally fine graphically because we're not talking about absolute maximum or minimum. So there wouldn't be an absolute max on this graph because we go to infinity. There would be an absolute minimum. But that's a totally different kind of concept than the relative maximums and minimums. So it is totally fine for a relative minimum to be bigger than a relative maximum. So don't be worried if your minimum numbers are bigger than your maximum numbers. And I also want to relate how this comes into play with increasing and decreasing. So relative minimums are always created by decreasing and then increasing. So you can see decreasing function, increasing function. So it's the point where we change from decreasing to increasing. Similarly, relative maximums are always created by going from increasing to decreasing. So it's the point at which we change from increasing to decreasing. So in order to find these intervals of increasing and decreasing, we're going to have to use the maximums and minimums. So let's see an example here. Find the intervals of increasing and decreasing. And then find the relative maxima and minima of the function. And as we learn more about graphing in this class, you will be able to graph these functions yourself. We're not at that point right now, so on your homework, you will be given a graph for these. This function looks like this. So you want to locate the maxima and minima. We have one maximum right here, and we have two minima right here. Those are going to be the changing points between increasing and decreasing. So you can see that we are decreasing in these two sections here, and we're increasing in these two sections here. So for our intervals of increasing, I like to use INC for increasing and DEC for decreasing, so I don't have to write them all out every single time. And then as a note, we always use soft brackets for increasing and decreasing. So we're going to do this section here, which is going to go from, that's decreasing, which is going to go from negative infinity to this point here. We're doing x values because we're going from left to right to -3. Union, then we're going to do this section here for decreasing. And that's going to go from -1. Remember, we always use the x value because we're going from left to right to 3. So that's our intervals of decreasing. And for increasing, we're going to do these two areas. So that's going to be from -3 to -1, union, and then the second area is going to start at 3 and go to infinity. You'll see that if you combine these two together, because we don't have any constant areas here, these are, you're going to get the entire function, the all real numbers here. Let's also find the maxima and minima. We have one maximum, and it's going to be this point here, the tallest in its little area there. So that's going to be, there's 3 ways that you can write this answer. So the important part is the y value. Like I said, we want to tell how tall the mountain is, not where the mountain is. So one way to answer this is 2. Another way, which is my favorite way to answer this, just so that I know what the point is, it would be f of -1 equals 2, but your actual answer is the 2. Or you can answer this as a point, -1, 2. As long as the y value is there, though, it would be a correct answer. So any of those 3 would be a correct answer. The minima are going to be these 2 points. So writing these in the way I prefer, you would say f of -3 equals -1, and f of 3 equals -5. But again, your answers are the -1 and the -5. So if you just write -1 and -5, that is totally fine. We will do a little bit more practice with these, but we're going to move on to talking about piecewise functions. Some functions are defined piecewise, using different output formulas for different parts of the domain. Piecewise functions are important because the real world doesn't act like a perfect math equation. So we take an econ problem, for example. In econ, our horizontal axis is usually going to be time. And over time, let's say maybe our demand equation looks like this. And then, uh-oh, something changes in our formula and it starts to look like this instead. And then, uh-oh, there's something else that's going to change. It starts to look like this. And then changes again, it looks like this. So we need to be able to have our equations change when the circumstances change in the real world. So that's why we get these functions which are defined differently for different parts of the domain. An example of a piecewise function, and say f of x equals, and then we use a curly brace to say all of these functions are put together. And the way we would write it is we write the 3 functions. So we have x plus 1, 3, and x squared. So those are our 3 functions that we're going to put together on a graph. And then you put a comma after them, and it's going to tell you the domain for which that function is true. So x plus 1 is true when x is less than -2. 3 is true when x is between -2 and 0. And x squared is true when x is greater than 0. We're going to go over graphing this in just a bit, but for now, I'm just going to give you the graph. So it's going to look like this. We have a point at -2, -1 there. Slope of -1, or slope of 1, sorry. And then in the middle, you have a y value of 3. And it's going to go between -2 and 0, like that. And again, we'll go over this more in just a little bit, but this problem is mostly just about seeing what these look like. So that's what this graph looks like. You can see this x plus 1 is for this section here. It's only for domain elements that are less than -2. And that's why we have an open circle on there, because it's strictly less than, not less than or equal to. The function y equals 3, the constant function, is going to be this middle one there. That's two closed circles because they're 2 or equal to's. And then last one, x squared, is going to look like this one here. Again, open circle at 0 because that's a strictly greater than, not a greater than or equal to. Then this problem on your homework is going to ask you to find the following. We're going to do f of -5, f of -2, f of -1, f of 0, and f of 2. So these work just like normal equations. When we plug in f of -5, we plug -5 into all of the x's in your equation. It's really important that you only plug the x into the appropriate domain though. So -5 is less than -2, which means it's not between -2 and 0, and it's not greater than 0. So that means the only function I'm allowed to plug this in, and there will always only be one that you can plug it into, is going to be that top function. So then I choose the top function and I'm going to plug it in just like I would normally. -5 plus 1 is -4. So f of -5 is -4. And you can see if we come over here to -5, you're going to end up on this first function here. You're not going to be on either of these two because those two aren't defined there. So now f of -2. Here you have to pay attention to the or equal to. So we can't plug it into this top one because this is not or equal to -2. We have to plug it into the second one where we are allowed to be equal to -2. So when we do this, this function, f of x equals 3. If we plug in x is -2, there's no x's to plug it into, so you're just going to get 3. So the y value in the middle there is going to be 3. And that should make sense again, because if you come to -2 on your graph, you're going to get this function here, which is always giving you a y value of 3. Again, -1 is between -2 and 0, so you're going to plug in and you get a y value of 3. And the same thing for 0, because this has the or equal to at 0. When you plug in 0, you're going to plug it into that second function, which is going to be 3. For f of 2, though, now we're greater than 0, which means we plug it into the last function. So that's going to be 2 squared equals 4. And again, that should make sense. If we come over here to 2, you're going to get a y value that's up there at 4 on that x squared graph. Now let's look at how to graph these yourself. We have f of x equals 1/3 x plus 3. On the domain, x is less than 3. And negative x on the domain, x is greater than or equal to 3. When you're graphing these yourself, to really kind of wrap your brain around what's happening, I would graph both functions separately, not even worrying about the domain. So I'm going to graph y equals 1/3 x plus 3 and y equals -x. So 1/3 x plus 3 has a y-intercept of 3, and a slope of 1/3. So I'm going to go up 1 over 3. Or if you'd rather go the other way, we go down 1, left 3. And either way you choose, you're going to get this line here. For y equals -x, you can always add 0. So that means our y-intercept is 0. And then we have a slope of -1, so we're going to go over 1, down 1. Or if you choose to go the other way, up 1, left 1. And so we're going to get this function here. Now that we have them graphed, we want to worry about the domains. So this one is for x less than 3. So it's really important that I find the special point. So I'm going to plug 3 into this function. So we have y equals 1/3 times 3 plus 3, which gives me y equals 1 plus 3 is 4. So I have a point, I plugged in 3 and I got 4 at 3 comma 4. So that point at 3 comma 4 is going to be an open circle because it's not or equal to. And then I'm going to use this like an arrow. I'm going to go to the left. So I'm going to only take this side of the function and I'm going to ignore the rest of it. So I'll go ahead and erase that. You can scribble it out or erase it while you're showing your work, whatever is easier for your brain to see. But this is what that piece of the function is going to look like. And same thing on this one. This one's only for x greater than or equal to 3. So again, I need to find the special point. So I'm going to plug in 3. And I get -3. So I have a point at 3, -3. So I'm going to go ahead and graph that. It's a closed circle this time because it is the or equal to. And then we're going to treat this like an arrow and it goes to the right. So you're going to ignore everything that's to the left. AKA, you're going to erase it. So I'm going to try to erase this without erasing too much of my graph. So it'll end up looking like this. Now we have the two pieces, so we can go ahead and put these on the plot together. So your answer graph is going to be both of these put together. And there's your answer. This would be the answer to the graph of this function. Let's try one with 3 functions in it, 3 pieces. We have x plus 2 with the domain as x is less than or equal to -5. -2 on the domain x is between -5 and 6. And 1/2 x for the domain x is greater than or equal to 6. Again, I'm going to graph all 3 pieces separately. This one's y equals x plus 2, y equals -2, and y equals 1/2 x. So we have y-intercept of 2 and a slope of 1. And go down 1 over 1 and get our graph that looks like this. The function y equals -2 is just a horizontal function which goes through y equals -2. The function 1/2 x, technically there's a plus 0, so your y-intercept is 0. We're going to go up 1 over 2 to get our slope of 1/2. And now I want to restrict the domains. So we have x is less than or equal to -5. And we need a point, so let's plug in -5. So we get y equals -3, which means we have a point at -5, -3. So it's going to be that point there. It's a closed circle, and the inequality points to the left. So we're just going to take the left-hand side of that function. For the middle one, the y value is always -2, so we don't really need to plug it in. We're just going to take our 2 points, which are open circles, and extend this a little bit. And then we're going to forget about everything that's outside. And then finally, for this last one, we have x is greater than or equal to 6. So when we plug in 6, we get 3. So we have a point at 6, 3. Which is a closed circle. And we're just going to take what's to the right. So we're going to erase everything that's not to the right. So when we put these all on a graph together, we get this. I'm just putting all of the pieces I just found on a graph together. And that would be your final answer. You just graphed this piecewise function. So a couple more examples we're going to do. We're also going to find increasing and decreasing stuff as well. Graph the following. And find the domain, range, and intervals of it increasing and decreasing. Part A is g of x equals x plus 2 for x less than or equal to 1 and x minus 3 for x greater than 1. Let's graph our pieces separately first. So x plus 2 has a y-intercept of 2 and a slope of 1. It's going to look like this. And x minus 3 has a y-intercept of -3 and a slope of 1. That one's going to look like this. Now let's restrict our domains, x less than or equal to 1. So I need to find my point at 1. So I plug in 1 for x. I get 3, which means I have a point at 1, 3. This one's going to be a closed circle because it is or equal to, and the arrow points to the left, so we're going to forget about everything that's not to the left. And for the second one, we have x greater than 1. So again, I'm going to plug in my 1 to figure out what the y value is. We get -2. So there's a point at 1, -2. This one gets to be an open circle because it is not an or equal to this time, and the arrow points to the right, so we're going to forget about everything that's not to the right. So now we put them on a graph together. And this is what our graph looks like. Now the problem wanted us to find the domain, the range, and then the intervals of increasing and decreasing. If there's constant as well, you should also do constant. But in this case, there's not. So for the domain, let's look at the domain of both of the functions. So this one here has y values for the x values of -infinity to 1. So you just want to think we go from -infinity and we stop having x values at 1. And that's a closed hard bracket because it's a closed circle. Then we're going to go this direction from 1. So that's union 1 to infinity. And you'll note that when you put these together, because there's a closed bracket on the 1, we're not actually skipping it. So your domain is going to be -infinity to infinity. So you can also think of this, if I drew a vertical line and I move it back and forth, there is no point at which this vertical line is not touching the function at least once. Now for the range, same thing applies. If I draw a horizontal line this time, there is no point at which that horizontal line is not touching the function. So the range is also going to be -infinity to infinity. So increasing is going to be the same thing because we have two sections for increasing. So just like the domain, we get -infinity to 1, union 1 to infinity. So that's going to end up being -infinity to infinity. And then there are no points on which this function is decreasing. So for decreasing, you write none. Let's do one more example. We have f of x equals 3x minus 2 for the interval x is less than -4, 1 for the interval -4 to 1, and x plus 2 for the interval x is greater than or equal to 1. Again, let's graph all three of these separately. We have y equals 3x minus 2, y equals 1, and y equals x plus 2. For the first one, we have a y-intercept of -2 and a slope of 3. So I'm going to go up 3 over 1, give myself this steep slope here. Y equals 1 is just a horizontal line which goes through y equals 1. And x plus 2 has a slope y-intercept of 2 and a slope of 1. It's going to look like that. Okay, our domain for the first one is x is less than, not less than or equal to, just less than -4. So let's plug in -4 to see where that point is. So you get y equals -12 minus 2 is -14. It's not quite on my graph, so I'm going to extend this a little bit. So we get -4, and I'm just going to say this down here, open circle is -4, -14, so I don't have to draw all the ticks. And we're only going to take things to the left. So we're going to cross out everything that's not to the left. So it's only this little area down here. For the middle one, the y value is always the same, so we're just going to take hard bracket -4 to open bracket -1. And then forget about everything that's not in between. And then for the last one, x is greater than or equal to 1, we need to plug in 1, which gives us 3. So we have a point at 1, -1, 3. This one's a closed circle because it is an or equal to, and the arrow points to the right. Now let's put these all in a graph together. So I need to get all the way down to -14. I'm just going to go by fives. So that's -5, -10, -15. That's going to be -4, -14 with an open circle. And then we draw a line. It's going to be a little bit steeper because it's a slope of 3. And then we have 1 with a closed circle that goes to +1 with an open circle. And then we have a point at 1, 3 and a slope of 1. So that is what this graph is going to look like. Now let's find our domain, range, and intervals of increasing and decreasing. And in this case, we do also have an interval of constant. So the domain again, these 2 points have circles filled in, so there's not actually any breaks here. So this is going to be from -infinity to infinity. The range is a little bit more difficult. So here, the range goes from -infinity to -14. Union, we're going to do the top real quick. This one goes from 3 to infinity. That one's a hard bracket. And then the hard part of this is not going to be on your test, so you don't need to stress about this. But the hard part is this section right here. We just have a 1 in the middle. And the way you do that is you use a curly brace to put that there's just a single point 1 there. Our intervals of increasing are going to be these 2 sections here. So using the domain, we have -infinity to -4. We always use soft brackets for increasing and decreasing. Union, 1 to infinity. And there are no points where we're decreasing, so you would put none there. But let's say I had a function coming down like this, like something like this, then I would have a decreasing section here. And then constant is this section in the middle. So that's just going to be from -4 to 1.